Tonight, every point of light in the deepest photograph ever taken is not a star. Each one is an entire galaxy. Hundreds of billions of stars packed into a faint smudge, smaller than a grain of sand held at arm's length. And in that one image alone, there are thousands of them. But here is what will truly break your brain. That photograph covers a patch of sky so tiny you could block it with a grain of rice. The rest of the sky stretches in every direction, filled with the same staggering density of galaxies as far as light can reach. When astronomers finally tried to calculate how many galaxies exist across the entire observable universe, the number was so enormous it forced them to rethink everything they believed about the cosmos. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something familiar. When you step outside on a clear night, away from city lights, and look up at the sky, you see stars. Thousands of them scattered across the darkness. Some bright, some faint, some clustering together in patterns we call constellations. But between those stars, between those pinpoints of light, there are dark patches. Regions of sky that look completely empty to your naked eye. No light, no stars, nothing. Just darkness. For most of human history, people assumed that darkness was exactly what it appeared to be. Empty space. A void between the stars where nothing existed. The universe, as far as anyone understood, was made of the stars you could see and nothing more. The dark gaps between them were just that. Gaps. Emptiness. The Milky Way was everything, and the darkness surrounding it was nothing. That assumption turned out to be spectacularly wrong. Those dark patches are not empty at all. They are filled with galaxies, not a few, not hundreds, not thousands, millions upon millions of galaxies, each one containing billions or even trillions of stars, each one so far away that all their combined light is too faint for human eyes to detect. You are looking directly at them when you gaze at those dark patches, but you cannot see them. They are hiding in plain sight, waiting for a telescope powerful enough to reveal what your eyes never could. But before we can understand how many galaxies fill the universe and why that number is so much larger than anyone expected, we need to understand what a galaxy actually is. Because the word gets used constantly, and it is easy to lose sight of what it truly means. A galaxy is a gravitationally bound system of stars, gas, dust, and dark matter. That is the technical definition, but let me unpack it because every part matters. Gravitationally bound means the components are held together by gravity. The stars are not just floating near each other by coincidence. They are locked together in a structure, orbiting a common center of mass, pulled inward by the collective gravity of everything in the system. Stars are the most visible component. They are the part that produces light, the part we can see across enormous distances. A galaxy can contain anywhere from a few million stars to several trillion. That range is staggering. The smallest galaxies, called dwarf galaxies, might hold only 10 million stars or so. The largest can contain several trillion. The Milky Way falls somewhere in the middle with an estimated 200 billion to 400 billion stars. Gas and dust are the raw materials from which new stars form. Clouds of hydrogen and helium, seeded with heavier elements produced by previous generations of stars, collapse under their own gravity to ignite new stars and planetary systems. Galaxies rich in gas can keep forming stars for billions of years. Galaxies that have used up or lost their gas stop forming stars, and gradually age as their remaining stars burn through their fuel one by one. Dark matter is the invisible scaffolding that holds it all together. We cannot see it directly because it does not emit or absorb light, but we know it is there because its gravitational effects are measurable. Stars and galaxies orbit faster than they should based on the visible matter alone. Something unseen is providing extra gravitational pull. That something is dark matter, and it makes up most of a galaxy's total mass, often outweighing all the visible matter by a factor of 10 or more. Galaxies come in different shapes. Spiral galaxies like the Milky Way have flat rotating disks with curving spiral arms where new stars are born. Elliptical galaxies are rounder and smoother, generally containing older stars and very little gas. Irregular galaxies have no clear shape, often because they have been disturbed by gravitational encounters with neighboring galaxies. But tonight, we are not cataloging galaxy types. We are asking a different and far more fundamental question. How many of these objects exist in the universe? And the answer to that question has a history that begins with confusion, proceeds through revolution, and leads to a number so enormous it challenges our ability to comprehend it. For thousands of years, humans looked up and saw a band of milky white light arching across the night sky. The ancient Greeks called it Galaxies, from their word for milk. Nobody knew what it was. It was simply a mysterious glow, a river of faint light with no obvious explanation. In 1610, Galileo Galilei pointed one of the earliest telescopes at this band of light and made a remarkable discovery. The glow was not a smooth, continuous sheet. It was made of individual stars, thousands upon thousands of them, packed so densely and lying so far away that they blurred together into a single luminous band for the unaided eye. This was the first evidence that the Milky Way was a vast collection of stars, far larger than anything humans had previously imagined. Over the next 2 centuries, telescopes grew larger and more powerful. Astronomers mapped more and more of the Milky Way, gradually understanding its structure and its enormous size. But along the way, they noticed something puzzling. Scattered across the sky were fuzzy patches of light that did not look like individual stars. Some were round and smooth. Some had distinct spiral shapes. Others were irregular and chaotic. Astronomers called these objects nebulae, from the Latin word for cloud. In the late 1700s, the astronomer William Herschel built some of the largest telescopes of his era and systematically catalogued thousands of these nebulae. The French astronomer Charles Messier had already compiled a famous catalogue of over 100 such objects, labeling them M1, M2, M3, and so on, to distinguish them from a comets he was hunting. But nobody knew what these fuzzy patches actually were, and a fierce scientific debate erupted that would take more than a century to resolve. Were they clouds of glowing gas within our own Milky Way, relatively close and relatively small? Or were they something far more extraordinary? Entire separate systems of stars lying at almost inconceivable distances beyond the boundaries of the Milky Way. The philosopher Immanuel Kant had speculated about the more radical possibility as early as 1755. He imagined that each spiral nebula might be a vast collection of stars, comparable in size to the Milky Way itself, separated from us by enormous gulfs of empty space. He called them island universes. It was a visionary idea, elegant and bold, but it remained pure speculation for generations. Nobody had the technology to prove it one way or the other. In 1920, the question reached its dramatic climax in what astronomers now call the Great Debate. Two prominent scientists, Harlow Shapley and Heber Curtis, argued opposite sides of the question in a public forum at the Smithsonian Institution in Washington. Shapley believed the Milky Way was the entire universe, and that the spiral nebulae were relatively small objects within it. Curtis believed the spiral nebulae were independent galaxies far beyond the Milky Way, each one a vast system of stars in its own right. Neither man had decisive evidence. The telescopes of the day were simply not powerful enough to settle the matter. The universe was keeping its secret. The answer came just 5 years later, and it arrived through one of the most important astronomical discoveries ever made. An astronomer named Edwin Hubble was working at the Mount Wilson Observatory in Southern California, using what was then the most powerful telescope in the world. A reflector with a mirror 100 inches across. Hubble turned this extraordinary instrument toward the Andromeda Nebula, the largest and brightest spiral nebula visible from the northern hemisphere, and accomplished something nobody had managed before. He resolved individual stars within it. This was critical. If Andromeda was simply a cloud of gas inside the Milky Way, you would not expect to see individual stars in it, but Hubble could see them. More importantly, he identified a particular type of star called a Cepheid variable. Cepheid variables are stars that pulsate in a regular rhythm, growing brighter and dimmer on a predictable cycle. Thanks to the groundbreaking work of astronomer Henrietta Leavitt, it was already known that the period of a Cepheid's pulsation is directly linked to its true brightness. A Cepheid that pulses slowly is intrinsically more luminous than one that pulses quickly. This relationship is extraordinarily useful for measuring distances. If you know how bright a star truly is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. The dimmer it appears compared to its actual luminosity, the greater the distance. It is the same principle behind why a flashlight appears dimmer the farther away you hold it. The light spreads out and its apparent brightness drops with distance. Hubble measured the pulsation period of a Cepheid variable star in the Andromeda Nebula and calculated its distance. The result was staggering. Andromeda was roughly 900,000 light-years away. The accepted size of the Milky Way at the time was about 100,000 light-years across. Andromeda was not inside the Milky Way at all. It was far beyond it. A completely separate galaxy, an entirely independent system of billions of stars lying at a vast distance from our own. His initial distance measurement was later revised significantly upward. Today we know Andromeda is about 2.5 million light-years away, much farther than Hubble originally calculated, because later astronomers refined the Cepheid distance scale and corrected errors in the calibration, but the fundamental conclusion was unshaken. Andromeda was a separate galaxy, and that single discovery, published in 1925, changed humanity's understanding of the cosmos forever. If Andromeda was a separate galaxy, then the other spiral nebulae were probably separate galaxies too. And they were. As telescopes improved throughout the rest of the 20th century, astronomers confirmed that the universe was filled with galaxies stretching out in every direction as far as instruments could see. The Milky Way was not the entire universe. It was one galaxy among many. The cosmos had expanded overnight from a single system of stars to something vastly, almost incomprehensibly larger. And the question that naturally followed was the question we are exploring tonight. How many galaxies are out there? This question turned out to be far harder to answer than anyone expected. You cannot simply look at the sky and count galaxies the way you might count stars in a constellation. Most galaxies are fantastically faint. They are billions of light years away, and their light has been traveling through space for so long that by the time it reaches Earth, it is unimaginably dim. The faintest galaxies detectable by modern instruments are millions of times dimmer than the faintest stars you can see with the naked eye. The only way to find them is with powerful telescopes and long exposure times. A camera attached to a telescope collects photons, particles of light arriving from distant sources. The longer you expose a camera to the sky, the more photons you gather, and the fainter the objects you can detect. A short exposure might reveal a handful of bright galaxies. A longer exposure reveals hundreds more. An even longer exposure reveals thousands of galaxies that were completely invisible in the shorter exposure. And here is the crucial point. There seemed to be no bottom to this well. Every time astronomers looked deeper, they found more galaxies. The universe kept revealing more of itself, and there was no sign it was running out. This realization set the stage for one of the most important astronomical observations of the 20th century. In 1995, the director of the Space Telescope Science Institute, an astronomer named Robert Williams, made a decision that many of his colleagues thought was reckless. He chose to point the Hubble Space Telescope at one of the emptiest, darkest, most featureless patches of sky anyone could find. A tiny region in the constellation Ursa Major that appeared to contain absolutely nothing of interest. No bright stars, no known galaxies, no nebulae, just pure blackness. And then he left the telescope staring at that patch for 10 consecutive days. To understand why this was controversial, you need to appreciate how precious telescope time is. Observing time on the Hubble Space Telescope is one of the most fiercely competed resources in all of science. Hundreds of astronomers submit proposals every year, each making detailed arguments that their target is the most scientifically important. Only a fraction of those proposals are approved. Every hour of Hubble's time is valuable beyond measure. And here was the director choosing to spend 10 full days, roughly 240 hours, staring at what appeared to be absolutely nothing. Some astronomers were openly critical. Others questioned whether anything useful could possibly come from pointing humanity's most expensive telescope at empty sky. The result silenced every critic. The image that came back is called the Hubble Deep Field, and it is one of the most stunning and consequential images in the history of science. That tiny patch of sky, a region so small you could block it entirely with a grain of sand held at arm's length, was not empty at all. It was packed with galaxies, roughly 3,000 of them, crammed into that minuscule sliver of darkness. Spirals, ellipticals, irregulars, galaxies of every conceivable shape and size, layered on top of one another across billions of light years of depth. Some were close enough that their spiral arms and bright cores showed clear structure. Others were so distant they appeared as nothing more than faint red smudges at the very edge of detection. Some of those faint smudges were galaxies, as they looked more than 10 billion years ago, their light having crossed most of the observable universe to reach the telescope's mirror. The scientific and emotional impact of this single image is hard to overstate. When the data was processed and the image assembled, researchers at the Space Telescope Science Institute gathered around their monitors and fell silent. They were looking at a photograph of nothing. Or rather, what everyone had assumed was nothing. And it was filled with galaxies, not scattered thinly across the frame, but packed densely, layered behind one another like a crowd stretching backward into a fog. The image made the cover of scientific journals. It appeared in newspapers around the world. It fundamentally changed the public understanding of the cosmos. For the first time, humanity had direct visual evidence that even the emptiest looking patches of sky are filled with galaxies. There is no direction you can look where galaxies do not exist. Every direction, every tiny patch of blackness is teeming with them. The darkness between the stars was never empty. It was full. But the Hubble Deep Field did more than simply reveal hidden galaxies. It provided a powerful method for estimating how many galaxies the entire observable universe might contain. And that method is elegantly simple in principle, even though the details become deeply complicated. Here is how the estimate works. The Hubble Deep Field covers a tiny area of the sky, about 5.3 square arc minutes. An arc minute is a unit of angular measurement. There are 60 arc minutes in 1 degree, and the full sky covers roughly 149 million square arc minutes. So the deep field image covers approximately 1/28 millionth of the total sky. Think about that for a moment. 1/28 millionth. It is like trying to judge the contents of an entire ocean by examining a single drop of water. If that one impossibly small patch contains about 3,000 galaxies, and if the rest of the sky has a similar density in every direction, then you can multiply. 3,000 galaxies times 28 million patches gives you roughly 84 billion galaxies. That was the first deep field estimate, a staggering number from a single observation of a single tiny patch of sky. But astronomers were cautious. One deep field might not be representative. Maybe that particular patch happened to be unusually crowded, or unusually sparse. The only way to check was to repeat the experiment in a completely different part of the sky. In 1998, astronomers did exactly that. They performed the Hubble Deep Field South, pointing the telescope at a similarly empty-looking region in the southern hemisphere. The result was essentially the same. About the same density of galaxies in a completely different direction. This was powerful confirmation. The original deep field was not a fluke. Galaxies really are distributed roughly evenly across the sky when you observe at large enough scales. Whatever direction you looked, however empty it appeared, the galaxies were there. Then, in 2004, astronomers went even deeper. Using Hubble's most advanced camera at the time, they collected light from a single tiny patch in the constellation Fornax for a total of about 11 days. The resulting image was the Hubble Ultra Deep Field, the deepest view of the universe ever captured at that time. It revealed about 10,000 galaxies in an area of sky even smaller than the original deep field. Some of these galaxies were so incredibly distant that their light had been traveling for over 13 billion years. It was reaching us from a time when the universe was barely 800 million years old, a time before most of the galaxies and stars we see today had even formed. The pattern was unmistakable. The original deep field had found 3,000 galaxies in one patch. The ultra deep field found 10,000 in a smaller patch by looking deeper. And every improvement in observation consistently revealed the same thing. More galaxies, always more galaxies. The universe was not running out. Every time the instrument improved, galaxies appeared where none had been visible before. The well had no bottom. In 2012, astronomers pushed further still with what they called the Hubble Extreme Deep Field. They combined a decade's worth of exposures of the same tiny region, layering image upon image, building up an extraordinarily deep composite that represented over 2 million seconds of total exposure time. That is more than 23 days of accumulated observation staring at a single point in the sky. The result revealed galaxies even fainter and more distant than the ultra-deep field had found. Some of the objects in that image emitted their light more than 13 billion years ago, when the universe was only about 500 million years old. An era when galaxies were just beginning to form from collapsing clouds of primordial gas. Each was faint, tiny, and unremarkable on its own, but together they reinforced the relentless conclusion. Every increment of depth produced more galaxies. The population simply kept going, deeper and deeper into the darkness. The ultra-deep field pushed the estimated galaxy count significantly higher. With more galaxies visible per unit of sky, the extrapolated total climbed to roughly 200 billion galaxies in the observable universe. This became the widely quoted number for over a decade. 200 billion galaxies. It appeared in textbooks. It was repeated in documentaries. It became one of those facts people memorize about the cosmos, a number so enormous that most people simply accepted it as the final word on the matter. But it was not the final word. And some astronomers already suspected it was far too low. The estimate of 200 billion galaxies counts only the galaxies that the Hubble Space Telescope can actually detect. It does not include galaxies that are too faint, too small, or too distant for even Hubble to see. And there are strong reasons to believe that those undetected galaxies vastly outnumber the ones we can observe directly. Consider the pattern. Every improvement in telescope capability has revealed more galaxies. The original deep field found 3,000 where astronomers expected nothing. The ultra-deep field found 10,000 in an even smaller area. The extreme deep field found fainter objects still by stacking years of exposure. Each time the instrument improved, the count grew. The universe was always hiding more galaxies below our detection threshold than it was showing above it. This pattern makes sense when you think about how galaxies are distributed by brightness. Luminous galaxies are relatively rare. These are the easy ones to spot. They show up even in shallow, short exposures. But for every large luminous galaxy, there are many more smaller, dimmer galaxies. Dwarf galaxies are the most common type of galaxy in the universe by a wide margin. They may contain only a few million to a few billion stars each. They are faint. They are small. And at great distances, they vanish below the detection limits of even our most powerful instruments. This is not a minor gap in our census. The galaxies we cannot see may outnumber the ones we detect by a factor of 5 or 10 or possibly even more. The visible galaxies, the ones that appear in our deepest images, might represent only the brightest tip of an enormous hidden population. Meanwhile, ground-based surveys were adding a different dimension. The Sloan Digital Sky Survey, which began regular operations in the year 2000, mapped roughly 1/3 of the entire sky and catalogued hundreds of millions of individual objects, including millions of galaxies. This survey could not see the faintest and most distant populations. It lacked the depth of the Hubble Deep Fields, but it covered an enormously wider area, providing a census of the brighter galaxy population across a vast expanse of sky. Combining both approaches gave astronomers a richer but still incomplete picture. Deep, narrow observations showed what lurks at the faintest brightness levels in tiny patches. Wide, shallow surveys showed how galaxies are distributed across huge regions. Together, they confirmed that the universe is saturated with galaxies at every scale, in every direction, at every distance that telescopes could reach. But both approaches shared the same fundamental limitation. They could only tally galaxies bright enough to detect. And the universe contains far more than any instrument has ever directly revealed. Imagine standing on a hilltop on a foggy night, looking out at a city below. You can see the brightest lights clearly. Skyscrapers with their rooftop beacons, stadiums blazing with floodlights, major intersections lit by powerful street lamps. You can count those lights, but the fog obscures everything else. The dim porch lights on residential streets are invisible. The headlights of cars on back roads are swallowed by the haze. The glow of a phone screen through a distant apartment window is far too faint to register. You know those lights exist because that is how cities work. You know from experience that dim lights vastly outnumber bright ones, but you cannot count what the fog hides from you. The universe presents exactly the same challenge. The bright galaxies are the skyscrapers. We can see them and count them directly. But for every bright galaxy in our images, there are potentially dozens or hundreds of faint dwarf galaxies lurking below the detection threshold. Physics and our models of galaxy formation tell us they must be there. But our telescopes are not sensitive enough to see them, especially when those faint galaxies lie billions of light years away, and their light has been dimmed and stretched by the expansion of space. The James Webb Space Telescope, which began scientific operations in 2022, has already started to confirm what many astronomers suspected. Webb operates primarily in infrared light, which allows it to detect types of galaxies that Hubble simply could not see. When light travels across billions of light years of expanding space, it gets stretched to longer wavelengths. Visible light from the most distant galaxies shifts into the infrared, becoming invisible to telescopes designed to see only visible light. Hubble had some infrared capability, but Webb was built from the ground up to observe the universe in infrared with unprecedented sensitivity and resolution. The early results have been remarkable. Webb is finding galaxies at distances that Hubble could never reach. Some of them formed within the first few 100 million years after the Big Bang, when the universe was still in its infancy. Many are small and faint, exactly the kind of objects that would be invisible to any previous telescope. And they are everywhere. Every deep observation with Webb reveals more galaxies than models predicted. But even Webb has limits. Its mirror is larger than Hubble's, but it is still finite. Its detectors are more sensitive, but they still have a noise floor below which faint galaxies disappear. There will always be objects too dim for Webb to detect. Just as there were objects too dim for Hubble, the pattern continues. Every new telescope finds more galaxies, but none of them finds all galaxies. This relentless increase in the galaxy count with every technological advance is itself a profound clue about the nature of the universe. It tells us something fundamental. The number of galaxies we observe is not a fixed property of the cosmos. It is a property of our instruments. Change the telescope and you change the count. Build a bigger mirror, develop a more sensitive detector, observe in a different wavelength, and galaxies appear where none was seen before. Every galaxy count ever published comes with an invisible asterisk. 200 billion galaxies is not the number of galaxies in the observable universe. It is the number of galaxies one particular telescope could detect in the observable universe. Those are very different statements. One claims to describe reality. The other describes what one instrument could see from one vantage point at one moment in the history of technology. The true number is almost certainly far larger, and determining what that larger number might be requires going beyond direct observation entirely. It means building mathematical models that estimate how many galaxies exist below the detection limits, how many are hidden by dust or lost in the glare of brighter neighbors, how many are simply too far away for their feeble light to register on any detector currently in existence. This is where the story shifts from simply looking at the sky and counting what appears to doing something far more challenging and far more interesting. Estimating the invisible, modeling the unseen, trying to determine the true population of galaxies across the entire observable universe, including the vast majority that no human eye and no human-built instrument has ever directly observed. And when astronomers finally attempted that calculation, when they tried to account not just for the galaxies they could see, but for all the galaxies that must exist below the detection threshold, the number they arrived at was not just somewhat larger than 200 billion. It was so much larger that it forced the scientific community to fundamentally rethink what they thought they knew about the structure of the cosmos. The darkness between the stars had never been empty, and the galaxies counted so carefully over the previous 2 decades turned out to represent only a fraction of the galaxies that truly exist. The universe was not hiding hundreds of billions of galaxies from us, it was hiding trillions. To understand why the true number of galaxies is so much larger than the number we can directly observe, you need to understand why most galaxies are invisible in the first place. And it is not just one reason. Several physical effects work together to push galaxies below the detection threshold of even our most powerful instruments, creating a hidden population that dwarfs everything any telescope has ever revealed in any photograph or survey. The most straightforward effect is the inverse square law. Light spreads out as it travels. When you double the distance between yourself and a light source, the source appears 4 times dimmer. Not twice as dim, 4 times. Move 10 times farther away, and it appears 100 times fainter. 100 times the distance, 10,000 times fainter. This relationship is merciless, and it applies to everything that emits light, from a candle on a table to a galaxy containing hundreds of billions of stars. Consider what this means at cosmic distances. A galaxy lying 1 billion light years away appears a certain brightness. That same galaxy at 2 billion light years would appear 4 times fainter. At 5 billion light years, 25 times fainter. At 10 billion light years, 100 times fainter. The light from that galaxy has been traveling through space for billions of years, spreading outward in all directions, dispersing itself across an ever-expanding sphere. By the time a minuscule fraction of that light reaches the telescope on or near Earth, it has been diluted to an almost unimaginable degree. A galaxy containing 100 billion stars, each one a blazing nuclear furnace, can appear as nothing more than a faint smudge, barely above the noise floor of the most sensitive detector ever built. And many galaxies are not even that bright to begin with. The most common galaxies in the universe are dwarfs, small collections of a few million to a few billion stars. They do not blaze across the cosmos with the luminosity of 100 billion suns. They glow dimly, modestly, like a distant porch light in a sea of darkness. Place a dwarf galaxy several billion light years away, and it vanishes completely. No detector in existence can pick it up. It is there, shining steadily with the light of millions of stars, but it might as well not exist as far as our instruments are concerned. But the inverse square law is only part of the problem. There is a second, more subtle effect that makes the situation far worse, and it arises from something fundamental about the universe we live in. The universe is expanding. Space itself is stretching. And this expansion does something strange and critically important to the light traveling through it. Light travels as a wave, and every wave has a wavelength. The wavelength of light determines its color. Short wavelengths produce blue and violet light. Longer wavelengths produce red and infrared light. Even longer wavelengths produce microwave radiation and radio waves. When light travels through a universe that is not expanding, its wavelength stays the same throughout the journey. The light arrives at its destination with the same color it had when it departed. The signal is preserved. But our universe is not static. It has been expanding since the Big Bang, and that expansion has never stopped. Every second, the fabric of space stretches by a tiny amount. And as space stretches, it stretches the light, traveling through it. Imagine drawing a wave on a rubber band with the peaks and troughs evenly spaced. Now slowly pull the rubber band from both ends. The wave does not break, but stretches. The distance between the peaks grows longer. The wavelength increases. That is precisely what happens to light traveling through our expanding universe. The wavelength of the light gradually increases as space stretches beneath it during the journey. The light gets pulled, not by any force acting on the photons themselves, but by the expansion of the space through which those photons are moving. This phenomenon is called cosmological redshift, and it is one of the most important effects in all of observational astronomy. The name comes from the fact that stretching a wavelength moves light toward the red end of the visible spectrum. Blue light shifts toward green, then yellow, then orange, then red. Red light shifts beyond what human eyes can see entirely, moving into the infrared. And infrared radiation shifts further still into the microwave and beyond. For galaxies that are relatively nearby, within a few 100 million light years, the redshift is small. Their light arrives slightly redder than it was when it left, but still well within the range of wavelengths that optical telescopes can detect without difficulty. But for galaxies billions of light years away, the effect becomes dramatic. Light that was originally emitted as visible light, the kind our eyes and optical telescopes were designed to detect, arrives at Earth as infrared radiation. It has been stretched completely out of the visible spectrum. An optical telescope pointed at that region of sky sees nothing. Not because the galaxy does not exist, but because the galaxy's light has been shifted to wavelengths the telescope was never designed to observe. The galaxy is there. It is shining. But it is shining in a color the telescope cannot see. The galaxy might as well be behind a wall. This is why infrared telescopes have become essential for studying the distant universe. They are specifically designed to capture exactly the kind of light that optical instruments miss. When the James Webb Space Telescope observes a galaxy 12 or 13 billion light years away, It is collecting photons that began their journey as ultraviolet and visible radiation, but have since been stretched into the infrared by the relentless expansion of space. Without infrared capability, entire populations of distant galaxies remain permanently hidden. Not because they are absent, but because their light has shifted beyond the reach of optical detectors. Different wavelengths reveal different populations. Observing in only one wavelength is like surveying a landscape with a filter over your eyes that blocks everything except one color. You will see whatever happens to be that color and miss everything else. And there's still another layer to this problem. Even after accounting for the inverse square law and cosmological redshift, there is a third effect that makes distant galaxies even harder to detect. It is called surface brightness dimming, and it is particularly cruel in its consequences. When a galaxy is nearby, it appears relatively large on the sky. You can see its structure, its spiral arms, its bright core, its dust lanes, and star-forming regions. The galaxy subtends a noticeable angular area on your detector, and the light is spread across many pixels. But as the galaxy moves farther away, its apparent size on the sky shrinks. At some point, the galaxy becomes so small that its light falls across only a few pixels on the detector, or even a fraction of a single pixel. Here is where the cruelty enters. Because the universe is expanding, the photons arriving from a distant galaxy do not just lose energy as their wavelengths stretch, they also arrive less frequently. The time between photon arrivals gets stretched out by the expansion of space, just as the wavelength does. The combined result is that the surface brightness of a distant galaxy, the amount of light per unit of angular area on the sky, drops far more steeply with distance than the inverse square law alone would predict. A galaxy that would be easily visible at 1 billion light years could be completely undetectable at 5 billion light years. Not just because it appears dimmer overall, but because its light has been diluted and spread so thinly across the detector that it drowns in the random electronic noise that every instrument produces. The galaxy is real, its photons are arriving, but the signal is so weak and so diffuse that no instrument can separate it from the background. These three effects, distance dimming, cosmological redshift, and surface brightness dimming, work in concert to create a vast population of galaxies that physically exist but remain undetectable with any technology currently available. And the problem is compounded enormously by the nature of the galaxies themselves, particularly the ones that filled the early universe. The universe today contains many impressive, luminous galaxies, grand spirals with sweeping arms and brilliant cores, massive ellipticals packed with trillions of old stars. These are the galaxies that show up prominently in surveys because they are big, they are bright, and many are relatively close. But the universe did not always contain these large systems. They were built over time through a slow process of merging and growth, and the building blocks they were assembled from were very different from the galaxies we see in the nearby universe today. In the first billion years after the Big Bang, the universe was filled with small, irregular, chaotic proto-galaxies. These were not grand spirals or massive ellipticals. They were tiny clumps of gas and young stars, often containing only a few million stars apiece. Some held perhaps 10 million. They had no defined spiral structure, no smooth elliptical shape. They were messy, compact, irregular blobs of intense star formation, flaring with the light of newly born stars burning hot and fast inside collapsing clouds of primordial gas. If you could somehow travel back in time and observe the universe as it was, 1 billion years after the Big Bang, you would see an entirely different cosmic landscape. Instead of a few 100 billion large prominent galaxies, you would see billions upon billions of these tiny flickering lights scattered across the darkness, each one small and faint, like fireflies spread across a vast field at night. The sky would look fundamentally different from the one we know. There would be no grand spirals with elegant curving arms, no massive ellipticals glowing with the soft red light of trillions of ancient stars. Just an overwhelming swarm of small, irregular shapes, each one glowing with the harsh blue-white light of freshly formed stars. Each one separated from its neighbors by gulfs of empty space, but connected to them by gravity that would eventually pull them together. The universe at that age was a construction site, raw and unfinished, the scaffolding visible everywhere, the final structures not yet assembled. Everything you see in the nearby universe today, every grand galaxy, every spiral, every giant elliptical, was still scattered across billions of these small building blocks, waiting to be combined through collisions that had not yet begun. Over billions of years, gravity pulled these small systems together. 2 proto-galaxies would collide and combine, their stars and gas mixing into a single, slightly larger galaxy. That larger galaxy would then merge with another, and another, each collision adding mass and stars to the growing structure. This hierarchical process of merging is how the large galaxies of the nearby universe were constructed, piece by piece over cosmic time. The Milky Way itself is the accumulated product of dozens of ancient mergers, stretching back more than 12 billion years. Every large galaxy you can observe nearby has a similar history. None of them appeared fully formed. They were all built gradually from smaller predecessors that no longer exist as independent objects. Now, here is the critical point for our question about galaxy numbers. In the early universe, before most of these mergers had occurred, the total number of individual galaxies was far larger than it is today. There were many more separate objects, but each one was far smaller and far fainter than the large galaxies we see nearby. At the enormous distances from which we observe those early epochs, those tiny dim proto-galaxies are almost completely invisible to current instruments. They existed. We can confirm this from the faint smudges that appear in our very deepest observations, and from the detailed predictions of our cosmological models. But the overwhelming majority of them fall below the detection threshold of any telescope currently in operation. They are out there, but we cannot see them. This is where astronomers employ one of their most powerful intellectual tools for estimating what they cannot directly observe. It is called a luminosity function, and understanding how it works is essential to grasping where the estimate of trillions of galaxies comes from. A luminosity function is a mathematical description of how many galaxies exist at each brightness level within a given volume of space. Imagine sorting every galaxy in a region of the universe by its luminosity and building a histogram. On one axis you have galaxy brightness, ranging from the most dazzling to the faintest. On the other axis you have the number of galaxies at each brightness level. When astronomers construct this histogram from their observations, a consistent pattern emerges every single time, regardless of which region of space they observe, or which cosmic epoch they examine. There are very few extremely luminous galaxies. These giants are rare. As you move to lower luminosities, the numbers increase. There are more medium brightness galaxies than bright ones, more faint galaxies than medium ones, and far more very faint galaxies than faint ones. The faint end of the distribution rises steeply, implying the dim dwarf galaxies vastly outnumber their brighter counterparts. Think of it like sorting the buildings in a city by height. There might be 5 skyscrapers taller than 50 stories, 20 buildings around 30 stories, 100 buildings around 10 stories, and thousands of small houses and structures only 1 or 2 stories high. The shorter the building, the more of them there are. Galaxies follow the same pattern. The dimmer the galaxy, the more common it is. And this pattern does not stop at the faintest galaxies we can see. It continues below the detection threshold, extending into a realm of ultra-faint objects that no telescope has ever directly captured, but that the mathematical curve tells us must be there. The mathematical form most commonly used to describe this brightness distribution was developed by the astronomer Paul Schechter in 1976. His formula, now called the Schechter function, captures the essential shape of the galaxy luminosity function. A gradual rise in galaxy numbers as you move to lower luminosities, followed by an exponential cutoff at the bright end where luminous galaxies become rare. The formula is governed by a few adjustable parameters, and the single most consequential parameter of all is something called the faint end slope. The faint end slope determines how rapidly the number of galaxies increases as you go to progressively lower luminosities. A steep slope means the count of faint galaxies rises very quickly, implying an enormous hidden population of dim dwarfs lurking below the detection threshold. A shallow slope means the increase is more gradual, and the hidden population, while still significant, is more modest. This one number, this single parameter describing the steepness of a mathematical curve, has enormous consequences for the total galaxy count. Adjust it upward by a small amount, and the estimated number of galaxies in the observable universe increases by hundreds of billions. Adjust it downward, and hundreds of billions disappear from the estimate. Measuring the faint end slope is one of the most demanding tasks in observational astronomy. It requires detecting the very faintest galaxies a telescope can possibly register, pushing instruments to their absolute sensitivity limits, and carefully distinguishing genuine faint galaxies from detector artifacts, background fluctuations, and other sources of contamination. The work is painstaking, technical, and inherently uncertain. Different surveys using different instruments observing in different wavelengths sometimes produce slightly different values for the faint end slope. And those seemingly small differences in the measured slope propagate into enormous differences in the total estimated galaxy count. Once the luminosity function has been measured down to the faintest directly detectable galaxies, astronomers do something bold. They extrapolate below the detection limit. They extend the mathematical curve beyond what they can directly observe, following its established trend into the realm of galaxies too faint for any instrument to see. This extrapolation is not a guess. It is a disciplined mathematical projection based on the shape of a curve that has been measured and confirmed across many different surveys, at many different distances, in many different wavelengths. Wherever astronomers have been able to measure the luminosity function, it follows the same form. The faint end keeps rising. There is no evidence at any observed brightness level of the curve flattening out or turning downward. As long as telescopes can detect fainter and fainter galaxies, they keep finding more and more of them per unit of brightness. The population grows as you go dimmer, and the extrapolation simply asks, What if this trend continues below the point where we can no longer see? If it does, the implications are enormous. Because the faint end of the curve rises so steeply, even a modest extension below the detection limit adds a very large number of galaxies to the total. And extending it further adds even more. The relationship is not linear. It is exponential in character. Each additional step downward in brightness adds not a few more galaxies, but many times more than the step before it. The detectable galaxies sit at the top of a distribution that widens rapidly beneath them, like the tip of a pyramid. The visible fraction is small. The hidden base is vast. This extrapolation is where the galaxy count explodes from hundreds of billions into the trillions. Because if the faint end slope continues at the rate measured above the detection threshold, then the number of galaxies below that threshold vastly exceeds the number above it. The detectable galaxies are the visible peak of a far larger distribution, like seeing the top of an iceberg while the enormous bulk lies beneath the water. In 2016, a team led by the astronomer Christopher Consolice at the University of Nottingham attempted the most comprehensive estimate yet of the total galaxy population across the observable universe. Their approach was ambitious and systematic. They combined deep survey data from multiple telescopes operating at different wavelengths. They measured galaxy number densities at multiple cosmic epochs, carefully determining how many galaxies existed per unit volume of space at different points in the universe's history. They constructed luminosity functions for each epoch, fitting the Schechter function to their data and pinning down the faint end slope at each distance. Then, they corrected for the galaxies too faint to detect, using the measured slope to extrapolate the luminosity function below the observation limits. Finally, they integrate these corrected densities across the full volume of the observable universe, adding up contributions from every epoch and every region of space to arrive at a single total. The result reshaped our understanding of the cosmos. The team estimated that the observable universe contains roughly 2 trillion galaxies. That is 10 times the previous consensus of 200 billion. The earlier count had captured only about 10% of the total population. 90% of all galaxies, 9 out of every 10, were too faint, too small, or too distant for even the deepest images to reveal. Let that settle for a moment. For over a decade, the number 200 billion had been treated as though it were the answer. It was printed in textbooks. It was repeated on television. It was cited in scientific papers. It became one of those cosmic facts that educated people could recite from memory. A tidy number that seemed to capture the enormity of the universe. And it was wrong. Not slightly wrong. Not off by a factor of 2, off by a factor of 10. The real number was not 200 billion. It was roughly 10 times larger. The universe had been hiding 90% of its galaxies from every telescope ever built. Think about what this means for every deep field image that had ever been published. The Hubble Deep Field, the Ultra Deep Field, the Extreme Deep Field, each one had been celebrated as the deepest view of the universe ever achieved. And each one had captured only a fraction of the galaxies that were actually present in that patch of sky. For every galaxy visible in those iconic images, roughly 9 others were there but invisible. They were below the detection threshold, too faint for even Hubble's extraordinary instruments to register. The famous images were real. Every galaxy in them was genuine. But they were like photographs of an iceberg taken from above the waterline. Spectacular and true, but showing only the part that rises above the surface, while the vastly larger mass remains hidden below. This was not a minor correction to the previous estimate. It was a fundamental revision of humanity's picture of the cosmos. The universe had not been slightly undercounted. It had been profoundly undercounted by a full order of magnitude, and the missing 90% consisted entirely of galaxies that no existing telescope could directly detect. Think about what this means in human terms. Every deep field image, every galaxy survey, every painstakingly compiled catalogue, all of this work spanning decades of observations by the most powerful telescopes ever constructed, had captured roughly 10% of the galaxies that actually exist within the observable universe. The remaining 90% were there all along, shining steadily with the light of millions or billions of stars, but too faint and too distant for any human technology to register. The universe had not been withholding a few extra galaxies. It had been withholding the overwhelming majority. Now it is essential to understand what this estimate is and what it is not. 2 trillion is not a precise count. It is an order of magnitude estimate, a carefully constructed approximation built on observations, mathematical models, and justified but ultimately uncertain extrapolations. Different research teams using different datasets and different assumptions about the faint end slope have arrived at somewhat different results. Some analyses broadly support the 2 trillion figure. Others suggest the number might be somewhat lower, perhaps closer to 1 trillion, because later studies with improved data revise the faint end slope slightly downward. Still, others argue the number could be higher. The uncertainty is genuine and, at this stage, irreducible. The most critical ingredient in the calculation, the faint end slope, sits right at the edge of what current instruments can measure. Small errors in characterizing the faintest detectable galaxies propagate into huge uncertainties in the total count. A slightly steeper slope adds hundreds of billions of galaxies. A slightly shallower one subtracts hundreds of billions. The difference between 1 trillion and 3 trillion galaxies hinges on the precise value of a single parameter that is extraordinarily difficult to determine. There is also an unavoidable question of definition. What counts as a galaxy? A massive spiral containing hundreds of billions of stars clearly qualifies. But what about a tiny gravitationally bound collection of 10 million stars orbiting in the halo of a larger galaxy? Is that a separate galaxy or merely a satellite? What about an even smaller clump of a few million stars? In recent years, astronomers have discovered ultra-faint dwarf galaxies so small and so dim that they blur the boundary between what we call a galaxy and what we might call a large star cluster. Where you draw that boundary affects the total count. Include every tiny gravitationally bound system and the number goes up. Restrict the definition to larger, more substantial systems and it comes down. The question of how many galaxies the universe contains partly depends on what you decide a galaxy is. What we can say with confidence is this: the observable universe contains somewhere between roughly 1 trillion and a few trillion galaxies, depending on how deep the observations go, what wavelengths are used, how the faintest populations are modeled, and where the definitional boundary is drawn. The old estimate of 200 billion was a tally of galaxies above a particular brightness threshold. The revised estimate of roughly 2 trillion attempted to include the vast modeled population below that threshold. Neither number is wrong in any simple sense, They answer slightly different questions about the same underlying reality. Future telescopes will continue to push the detection threshold lower, pulling more galaxies into view. The Nancy Grace Roman Space Telescope will survey enormous areas of sky in infrared light, potentially uncovering populations of faint galaxies that current instruments miss because of their narrow fields of view. The Vera Rubin Observatory will map billions of objects across the visible sky, building the most comprehensive census of the nearby galaxy population ever attempted. Each new instrument will detect galaxies that no previous telescope could see, but none of them will detect everything. The pattern that has held throughout the entire history of astronomy will almost certainly continue. Every improvement in technology reveals more galaxies, and the universe always keeps more hidden below the new threshold. The galaxies we directly observe in our deepest photographs are not the full story. They are the detectable fraction of a much larger whole. Like seeing only the tallest peaks of a mountain range above a thick layer of cloud while the foothills and valleys remain completely hidden. The visible galaxies are the luminous summits of a population that extends far below our ability to see. The full extent of this hidden population is something we can estimate through mathematical modeling, but may never know with certainty. The universe we observe through our telescopes is real and rich and staggeringly vast, but it is also unavoidably incomplete. What the research of the past decade has shown is that the darkness between the stars was never empty. It was filled with galaxies, far more of them than anyone imagined. And the galaxies that do appear in our deepest images, the ones we can count and catalogue and study, represent only a fraction of the true population. For every galaxy bright enough to register in a deep field photograph, there are many more lurking just below the detection limit. Faint dwarfs and distant proto-galaxies that a slightly more powerful instrument would have revealed. And below those, fainter still, there are more. The population extends downward into dimness with no clear bottom, always more than what is visible at the surface, always hiding more than it shows. And this raises a question that makes the counting problem even more complex than it already appears. If galaxies merge and evolve throughout cosmic history, if the early universe contained billions of small proto-galaxies that have since been swallowed and consolidated into the larger galaxies we see today, then the total number of galaxies is not a fixed quantity. It changes over time. The universe, 13 billion years ago, did not contain the same number of galaxies it contains right now. The population has been transforming throughout the entire history of the cosmos, and understanding how and why that number changes is the next critical piece of this puzzle. There is something about counting galaxies that most people never consider, and once you understand it, the entire question of how many galaxies exist becomes far more complicated than it first appears. The number is not fixed. It is not a single answer carved into the fabric of the cosmos for all time. The number of galaxies in the universe changes. It has been changing since the universe began, and it is still changing right now while you are listening to these words. Galaxies are not eternal, unchanging objects. They are born, they grow, they collide and merge and consume one another. 2 galaxies become 1, 3 become 2. Over billions of years, the total population of separate individual galaxies decreases even as the surviving galaxies grow larger and more massive. The universe today does not contain the same number of galaxies it contained 5 billion years ago, or 8 billion years ago, or 12 billion years ago. and understanding why that number changes is essential to understanding what any galaxy count actually means. But before we can explore how the galaxy population evolves over time, we need to confront one of the most profound and sometimes overlooked facts about observational astronomy. When you look at a distant galaxy, you are not seeing it as it exists right now. You are seeing it as it existed in the past. This is not a limitation of our telescopes. It is a fundamental consequence of the speed of light. Light is fast. It travels at roughly 300,000 kilometers per second. But it is not instantaneous. It takes time to cross the distances between objects in the universe. Light from the moon takes about 1.3 seconds to reach Earth. Light from the sun takes about 8 minutes and 20 seconds. Light from the nearest star beyond the sun, Proxima Centauri, takes 4.24 years. These are tiny delays from a cosmic perspective, but they establish an inescapable principle. Every observation of a distant object is an observation of that object's past, not its present. The image you receive is always a record of what the object looked like when the light departed, not what it looks like now. For galaxies, this effect becomes enormous. A galaxy 1 billion light years away is seen as it was 1 billion years ago. A galaxy 5 billion light years away is seen as it was 5 billion years ago. A galaxy 12 billion light years away is seen as it was 12 billion years ago, when the universe was less than 2 billion years old, when the cosmos was a fundamentally different place than it is today. The deeper you look into space, the further you look into the past. Distance and time become inseparable. Every telescope is a time machine, and the images it produces are not snapshots of the present universe. They are a layered composite of many different eras, all arriving at the detector simultaneously, each layer representing a different moment in cosmic history. This is both a gift and a complication. It is a gift because it allows astronomers to directly observe the universe at different stages of its evolution. By looking at galaxies at various distances, we can literally watch how galaxies change over billions of years. Nearby galaxies show us the universe as it is today. Galaxies at moderate distances show us the universe as it was several billion years ago. The most distant galaxies show us the universe in its infancy. No other science has this ability. Geologists can study rock layers. Archaeologists can dig through ruins. But astronomers can look across billions of years of history simply by pointing their telescopes in different directions and collecting light that depart at different times. But this is also a complication for counting galaxies. Because when you survey the sky and count every galaxy you can detect, you are not counting galaxies as they exist at one single moment. You are counting galaxies as they existed at many different moments. The nearby galaxies in your survey represent the present epoch. The moderately distant ones represent the universe as it was billions of years ago. The most distant ones represent the universe when it was very young. Your census is mixing together populations from completely different eras of cosmic history, each era containing a different number of galaxies with different sizes and different properties. Astronomers call the time it takes for light to travel from a distant object to us the look-back time. When the look-back time is small, you are seeing the universe roughly as it is now. When the look-back time is large, you are peering deep into the past. And as you look further back in time, you encounter a universe that was very different from the one we inhabit today. In the very early universe, within the first billion years after the Big Bang, there were no large galaxies. There were no grand spirals with sweeping arms, no massive ellipticals packed with trillions of old stars. What existed instead were enormous numbers of small, compact, irregular proto-galaxies. These were tiny systems, often containing only a few million stars. Some held perhaps a few tens of millions. They were clumpy and chaotic, bursting with the light of hot young stars, forming rapidly from clouds of primordial hydrogen and helium. Many were no larger than what we would now classify as dwarf galaxies. But they were everywhere, filling the young cosmos in vast numbers that dwarfed the galaxy populations we see in the nearby universe today. These early proto-galaxies were the building blocks of everything that followed. Over time, gravity drew them together. Two small systems would drift close enough for their mutual gravitational attraction to pull them into a collision. The collision was not like two cars crashing. Stars within galaxies are separated by such enormous distances that when galaxies merge, individual stars almost never hit each other. Instead, the two systems pass through each other, their gravitational fields intertwining, their orbits disrupted, their structures distorted. Gas clouds within the merging galaxies collide and compress, triggering intense bursts of new star formation. Over hundreds of millions of years, the two galaxies lose their individual identities and settle into a single combined system, larger and more massive than either of the originals. This process repeated billions of times across the early universe. Two proto-galaxies became one. That merged galaxy later collided with another, growing larger still. Gradually, over billions of years, the enormous population of small proto-galaxies was consolidated into a smaller population of progressively larger galaxies. The total number of individual galaxies decreased, but the average size of each surviving galaxy increased. It was like starting with a beach covered in billions of tiny sand grains and slowly pressing them together into a smaller number of larger pebbles. Each pebble contains the material of thousands of former sand grains. The total amount of matter stays the same, but the number of separate objects drops dramatically. This process is called hierarchical galaxy formation, and it is one of the foundational principles of modern cosmology. Large galaxies are not born large. They are assembled gradually from smaller predecessors through repeated mergers over cosmic time. The evidence for this process is overwhelming. Computer simulations that model the evolution of the universe from shortly after the Big Bang to the present day consistently reproduce this behavior. Starting with small density fluctuations in the early cosmos, gravity pulls matter together into small clumps, and those clumps merge over billions of years into progressively larger structures. The simulated universe develops galaxy populations, sizes and distributions that closely match what we observe in the real sky. The theory works. Observational evidence also supports hierarchical formation directly. When astronomers look at galaxies at large look-back times, they find that galaxies are smaller, more numerous, and more irregular than nearby galaxies. This is exactly what the merger scenario predicts. The early universe should contain many small building block galaxies. The nearby universe should contain fewer but larger galaxies, because merging has consolidated the population. And that is what we see. The pattern is consistent across every deep survey ever conducted. More small galaxies in the past, fewer large galaxies in the past, fewer total galaxies in the present, more large galaxies in the present. Our own Milky Way is a product of this process. The galaxy you live in was not a single object that formed all at once. It was assembled from dozens of smaller galaxies that merged over more than 12 billion years. Astronomers have identified the remnants of some of these ancient mergers embedded within the Milky Way's structure. The Gaia Enceladus galaxy, sometimes called the Gaia sausage structure, because of the elongated shape its stars trace in certain orbital diagrams, was a substantial dwarf galaxy that collided with the early Milky Way roughly 10 billion years ago. Its stars are still identifiable today. They orbit through the Milky Way's halo on distinct trajectories that differ from the orbits of stars born within the Milky Way itself. By analyzing the chemical compositions and orbital properties of these stars, astronomers have reconstructed the history of this ancient collision. The Gaia Enceladus galaxy was absorbed completely. It no longer exists as a separate galaxy. Its stars are now part of the Milky Way. Two galaxies became one, and the total galaxy count of the local universe dropped by one. And that was not an isolated event. The Milky Way has consumed many smaller galaxies throughout its history. The Sagittarius dwarf elliptical galaxy is being consumed right now. It is a small galaxy that orbits the Milky Way, and with each pass, the Milky Way's gravity strips away more of its stars. Over the next few 100 million years, it will lose its identity entirely, its remaining stars scattered into the Milky Way's halo. One more galaxy will disappear from the census. One more merger will reduce the total count by one. Looking further into the future, the Milky Way itself will undergo an even more dramatic transformation. The Andromeda Galaxy, the nearest large spiral galaxy, is approaching the Milky Way at roughly 110 kilometers per second. In approximately 4.5 billion years, the two galaxies will collide and begin a lengthy merger process. Over the course of another billion years or more, the two spirals will blend into a single large elliptical galaxy. Astronomers have informally nicknamed this future galaxy Milkdromeda. When the merger is complete, two of the largest galaxies in the local group will have become one. The number of large galaxies in our cosmic neighborhood will have decreased. The pattern that has been operating since the first billion years of cosmic history, the steady consolidation of many smaller galaxies into fewer larger ones, will claim two more entries from the ledger. This ongoing process of merging and consolidation is why the question of how many galaxies exist does not have a single permanent answer. The answer depends on when you ask. At the present cosmic epoch, the observable universe contains somewhere between roughly 1 trillion and a few trillion galaxies, depending on how deeply you observe and how you define a galaxy. But if you asked the same question 8 billion years ago, the answer would have been larger. More individual galaxies existed because many of the mergers that reduced the count had not yet occurred. If you asked 12 billion years ago, the answer would have been larger still. The early universe teemed with proto-galaxies that have since been consumed and incorporated into the bigger structures we see today. The 2016 study by the University of Nottingham team that estimated roughly 2 trillion galaxies explicitly accounted for this time evolution. Part of the reason their number was so much larger than the previous consensus of 200 billion was precisely because they included the enormous early population of small galaxies that existed at high look-back times. Many of those galaxies no longer exist as separate objects. They have merged into larger galaxies by the present day. But they were real galaxies at the time, And if you are tallying the galaxy population of the observable universe across all epochs, across all the look-back times captured in a single deep observation, those ancient galaxies contribute to the total. This raises a subtle but important distinction that is often lost in popular reporting. When someone says the observable universe contains 2 trillion galaxies, what exactly does that mean? Does it mean 2 trillion galaxies exist right now, at this very moment, spread across the cosmos? Or does it mean 2 trillion galaxies have existed at various points in cosmic history, and are captured at various stages in our observations, many of which have since merged into larger systems? The answer is closer to the second interpretation. The 2 trillion figure includes galaxies observed at high redshift, galaxies whose light has been traveling for billions of years, galaxies that no longer exist as independent objects because they have since been absorbed by mergers. The number of galaxies that exist right now at the present cosmic moment is almost certainly smaller than 2 trillion because mergers have reduced the population over time. Here is a way to think about this. Imagine photographing a busy city street, but with a camera that works unlike any camera you have ever used. Instead of capturing everyone at the same instant, this camera captures each person at a different moment in history, depending on how far away they are standing. The person right in front of you is captured as they look today. The person 50 feet away is captured as they looked a year ago. The person a block away appears as they were a decade ago. Someone standing at the far end of the street appears as they were a century ago, wearing clothes from a bygone era, perhaps no longer alive. You press the shutter once, and a single image comes back containing people from dozens of different eras, all sharing the same frame, but none of them existing at the same moment. If you count every person in that photograph, you get a number. But that number does not tell you how many people are standing on the street right now. It tells you how many people appeared on the street across many different moments in time, blended together into one composite image. Some of those people are still alive and still standing there. Others died long ago, but their image persists in the photograph because the light capturing their likeness traveled slowly enough that it arrives at the camera alongside light from people who are alive today. That is what a galaxy survey does. It captures galaxies from many different cosmic eras in a single observation. The nearby galaxies are contemporary. The distant galaxies are ancient. Some of those ancient galaxies no longer exist as separate objects. They merged with neighbors billions of years ago, but their light is still arriving, so they appear in the photograph, contributing to a count that mixes the living and the long since absorbed into a single number. But quantifying the present-day number is itself complicated. We cannot observe the present-day state of distant galaxies. When we look at a galaxy 10 billion light years away, we are seeing it as it was 10 billion years ago. We have no way of knowing what that particular galaxy looks like right now, or even if it still exists as a separate galaxy. It might have merged with a neighbor 5 billion years ago and been absorbed into a larger system. We can only see its past. Its present state is hidden from us by the finite speed of light. This creates a fundamental asymmetry in our knowledge. We can directly observe nearby galaxies in their current state and distant galaxies in their past states. But we cannot observe distant galaxies in their current states. To estimate the present-day galaxy population, astronomers must use models, simulating how galaxy mergers would have continued over the billions of years between the observed epoch and the present day. These simulations are sophisticated, and they produce reasonable estimates, but they are estimates. They carry uncertainties. Different models with slightly different merger rates produce different present-day populations. This is one of the reasons why no single galaxy count should be treated as a definitive final answer. The number depends on at least 3 things that are genuinely uncertain. First, how deeply you observe, which determines how many faint galaxies you detect or model statistically. Second, what cosmic epoch you are asking about, because the total changes over time as galaxies merge and form. Third, what you define as a galaxy, because the boundary between the smallest galaxies and large star clusters is blurry and somewhat arbitrary. The honest scientific answer is not a single precise number. It is a range. The observable universe contains somewhere between hundreds of billions and a few trillion galaxies, depending on the assumptions and definitions used. This might seem unsatisfying. You might want a single clean number, a definitive count that settles the question once and for all. But the universe does not offer that kind of certainty on this question. The galaxy population is a dynamic, evolving quantity that depends on how you observe, when you observe, and what you choose to count. Any single number you encounter, whether it is 200 billion or 2 trillion, is a snapshot of one set of assumptions at one moment in the history of astronomical research. What astronomers can say with confidence is this: the true number is very large. It is almost certainly far larger than what any telescope has directly detected, and it has been changing throughout the entire history of the universe, shaped by the relentless gravitational process of merging that has been consolidating small galaxies into larger ones since the first structures formed from the primordial fog of hydrogen and helium. The merging process also explains something else that occasionally confuses people. Why do some popular accounts say there are 200 billion galaxies, while more recent accounts say 2 trillion? This sounds like one of them must be wrong, but that is not quite right. The 200 billion figure was an estimate of the galaxies directly detectable by telescopes available at that time. The 2 trillion figure attempted to include the far larger population of galaxies below the detection threshold, including the vast numbers of small proto-galaxies that populated the early universe but have since merged out of existence. They are not really contradicting each other. They are answering slightly different versions of the same question, one counting what can be seen, the other estimating what exists, including what cannot be seen. And even the 2 trillion figure is not necessarily the final word. As newer telescopes push deeper into the infrared, as survey capabilities expand, as models of galaxy formation and evolution become more sophisticated, the estimate will continue to evolve. It might go up. It might go down somewhat as certain assumptions are refined. The history of this question shows a consistent pattern. Each generation of instruments reveals that the universe contains more galaxies than the previous generation could detect. There is no reason to assume this pattern has stopped. Future observatories may find that even 2 trillion is an undercount, that the faint end of the luminosity function extends further than current models predict, and that the true population is larger still. But there is a limit to how much further the number can grow. Below a certain mass threshold, gravitationally bound collections of stars may not form or survive in significant numbers. The dark matter halos that serve as scaffolding for galaxy formation have a minimum mass below which they cannot efficiently accumulate gas and form stars. Somewhere at the extremely faint end of the luminosity function, the population must eventually decline. There must be a bottom to the distribution, a point below which galaxies simply do not form. We do not know exactly where that floor is, but it almost certainly exists. The number of galaxies is very large, but it is not infinite. What we are left with is a picture that is both humbling and awe-inspiring. The universe began with vast numbers of small proto-galaxies, each one a tiny flickering light in the primordial darkness. Over billions of years, gravity sculpted these raw materials into the galaxies we see today, pulling small systems together, building larger and larger structures through collision after collision. The total count of separate galaxies decreased steadily as mergers consolidated the population. At the same time, the surviving galaxies grew more massive, more luminous, more structured. The chaotic clumps of the early universe gave way to the elegant spirals and massive ellipticals of the present cosmos. The universe we observe today is the result of this long gravitational evolution. The galaxies that appear in our deepest photographs are not the original population. They are the survivors, the products of billions of years of merging and growth. And the population is still evolving. Mergers are still happening. Galaxies are still colliding and combining. The Milky Way is still consuming smaller satellites. The Andromeda collision is still approaching. Billions of years from now, the universe will contain even fewer galaxies than it does today, each one larger, each one carrying the accumulated mass of many predecessors that have lost their separate identities forever. When you hear that the universe contains trillions of galaxies, it is worth remembering that this number is not carved in stone. It is a number that has been changing since the cosmos began and will continue changing for billions of years to come. The galaxy population is alive in a sense, not static, not permanent, but evolving, dynamic, shaped by the fundamental force of gravity operating across cosmic scales and cosmic time. The universe is not a fixed collection of objects sitting unchanging in the void. It is a process, and the galaxies we see, the galaxies we count, the galaxies we try so hard to tally, are moments in that process, captured in light that has crossed unimaginable distances to reach us, each photon carrying a message from a different point in the universe's long and still unfolding history. But even all of this, the faint populations hiding below the detection threshold, the ancient proto-galaxies that have merged out of existence, the evolving count that changes with every cosmic epoch, even all of this concerns only the galaxies within the observable universe, the region of space from which light has had time to reach us since the Big Bang. And the observable universe, vast as it is, might not be the entire story. Beyond it, beyond the farthest light we can ever hope to detect, there might be far more universe than we have ever seen or ever will see. And that possibility opens a question even more dizzying than the ones we have explored so far. Everything we have discussed so far, the deep field observations, the luminosity functions, the corrections for faint populations, the evolving galaxy count across a cosmic time, all of it applies to one particular region of the cosmos, the observable universe. This is an important distinction, and it is one that most people either overlook or do not fully appreciate. The observable universe is not the universe, it is the part of the universe we can see, and the difference between those two concepts is enormous, possibly infinite. The observable universe has a boundary, not a physical wall or a barrier you could touch, but a horizon, a limit defined by the speed of light and the age of the cosmos. The universe is roughly 13.8 billion years old. Light travels at a finite speed, about 300,000 kilometers per second. Since the Big Bang, light has had 13.8 billion years to travel through space. You might assume this means we can see 13.8 billion light years in every direction. But that is not quite right, because the universe has been expanding the entire time. When a photon left a distant galaxy early in the universe's history, that galaxy was relatively close. But while the photon traveled toward us, space expanded. The galaxy was carried farther and farther away by the stretching of space itself. By the time the photon finally arrives at our telescopes, the galaxy that emitted it is no longer 13.8 billion light years away. It is much farther. Astronomers have calculated that the most distant objects whose light can reach us are now approximately 46.5 billion light years away in every direction. This makes the full diameter of the observable universe roughly 93 billion light years. This might sound like a contradiction. How can we see something 46.5 billion light years away if the universe is only 13.8 billion years old? The answer is that the galaxy was much closer when the light left it. The light was able to begin its journey across a reasonable distance. But during the billions of years that the light was in transit, the expansion of space stretched the distance between the source and the destination. The photon kept traveling at the speed of light through locally static space, but the total distance it needed to cover kept increasing because space itself was growing. By the time the photon reaches us, the galaxy that emitted it has been carried to an enormously greater distance than where it started. This expansion is not galaxies flying through space like shrapnel from an explosion. It is space itself stretching. Imagine dots drawn on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot. The dots are not sliding across the surface. The surface itself is expanding, carrying the dots with it. Galaxies in the real universe behave the same way. They are not rocketing through space at high velocities. They are roughly stationary in their local regions of space. But the space between them is growing, and the cumulative effect over billions of light years is that distant galaxies are receding from us at tremendous speeds. For galaxies that are far enough away, the recession speed exceeds the speed of light. This does not violate any law of physics. Nothing is moving through space faster than light. The galaxies are sitting still in their local space. It is the space between us and them that is expanding faster than light can cross it. The result is a hard limit on what we can observe. Light from those galaxies cannot reach us. It is trying to cross the gap, but the gap is growing faster than the light can close it. Those galaxies are forever beyond our reach. Their light will never arrive. No improvement in telescope technology, no matter how dramatic, can ever bring them into view. They are not hidden by distance or faintness. They are hidden by the fundamental geometry of expanding space. This means the observable universe has a true horizon, a boundary beyond which observation is not merely difficult, but physically impossible. Everything inside that horizon is in principle detectable, given a sufficiently powerful telescope and enough time. Everything outside it is permanently, irrevocably invisible, but the universe does not stop at that boundary. There is no reason to believe that space ends at the edge of our observable volume. The laws of physics, as far as we can determine, are the same everywhere. The universe on the larger scales appears uniform. It looks roughly the same in every direction, with the same density of matter, the same types of galaxies, the same large-scale structures. This property, called the cosmological principle, suggests that the universe beyond our horizon looks much like the universe within it. More space, more galaxies, more of the same structures extending outward in every direction. How much more? This is one of the deepest unanswered questions in all of cosmology, and the honest answer is that we do not know. The universe beyond the observable horizon might extend for another few billion light years, making the total universe modestly larger than what we can see. Or it might extend for trillions of light years, or it might extend forever. It might be infinite. The geometry of space provides some clues. Astronomers have measured the overall curvature of the universe by studying the patterns in the cosmic microwave background, the faint radiation left over from the earliest epoch of the cosmos. The cosmic microwave background is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, at the moment when the universe had cooled enough for atoms to form and for light to travel freely for the first time. Before that moment, the universe was a dense fog of charged particles. Light could not travel more than a short distance without being scattered. The universe was opaque. After atoms formed, that fog cleared, and light was free to travel unimpeded across the cosmos. The photons released at that moment have been traveling ever since, and we detect them today as a faint glow of microwave radiation coming from every direction in the sky. This radiation was first detected in 1965 by Arno Penzias and Robert Wilson, who initially mistook it for antenna noise before realizing they had stumbled upon one of the most important discoveries in the history of physics. The cosmic microwave background is not just a curiosity. It is a map of the universe as it existed 380,000 years after the Big Bang. The tiny temperature variations in this radiation correspond to slight density differences in the early cosmos, the same density fluctuations that eventually grew through gravitational collapse into the galaxies, clusters, and superclusters we see today. By analyzing the statistical patterns of these fluctuations, their sizes, their spacings, their correlations, astronomers can extract precise information about the overall geometry of the universe. And what those measurements show is striking. The universe appears to be flat. Not flat like a table, but flat in the mathematical sense. The angles of a triangle drawn across billions of light years add up to exactly 180 degrees, just as they do on a flat piece of paper in high school geometry. If the universe had positive curvature, like the surface of a sphere, those angles would add up to more than 180 degrees. If it had negative curvature, like a saddle shape, they would add up to less. The fact that the measurements consistently return a flat geometry to within the precision of current instruments has profound implications. A flat universe can be either finite or infinite. There are mathematical constructions where a flat space wraps around on itself like a torus and has finite volume. But the simplest interpretation of a flat geometry, and the one that most cosmological models adopt, is that the universe is infinite. It extends forever in every direction without boundary or edge. If this is correct, then the observable universe with its 93 billion light-year diameter is a tiny bubble within an infinitely larger cosmos. And the galaxies within our observable volume are an infinitesimally small fraction of the galaxies that exist in the full universe. Think about what this means for the galaxy count. If the observable universe contains roughly 2 trillion galaxies, and if the universe extends far beyond what we can see, then the total number of galaxies in the actual universe could be staggeringly larger. If the universe is 10 times the diameter of the observable volume, the total volume would be 1,000 times greater, and there could be roughly 2 quadrillion galaxies. If it is 100 times larger, the total swells to 2 quintillion. And if the universe is truly infinite, then the number of galaxies is also infinite. 2 trillion becomes not the total, but an unimaginably small fraction of a total that has no upper bound. The observable universe, vast and overwhelming as it seems, would be nothing more than a droplet in an ocean without shores. Even if the universe is not infinite, even if it has some enormous but finite extent, the observable volume is almost certainly a small fraction of the whole. Various analyses based on cosmological data suggest the total universe is at minimum several hundred times larger in radius than the observable portion. Some models place the lower bound even higher. At these scales, the 2 trillion galaxies within our observable horizon represent a tiny sample of a much larger population. This distinction between the observable universe and the total universe is essential for understanding what any galaxy count actually means. When astronomers say the observable universe contains roughly 2 trillion galaxies, that number applies only to the volume from which light has been able to reach us. It says nothing about what lies beyond. The total population of galaxies in the entire universe could be trillions of trillions, or it could be infinite. We have no way of measuring it directly, and we may never have such a way. The boundary of the observable universe is not a temporary limitation that better technology will overcome. It is a permanent feature of the cosmos, set by the finite speed of light, the finite age of the universe, and the accelerating expansion of space. And that expansion is accelerating. This is one of the most surprising discoveries of the past few decades. In 1998, 2 independent teams of astronomers studying distant supernovae found that the expansion of the universe is not slowing down, as most physicists had expected. It is speeding up. Something is pushing space apart at an ever-increasing rate. Astronomers call this phenomenon dark energy, though the name is a placeholder for our ignorance. We do not know what dark energy is. We can measure its effects, we can describe it mathematically, but we do not understand its fundamental nature. Dark energy has a direct and unsettling consequence for the future of our observable universe. Because the expansion is accelerating, galaxies beyond a certain distance are being carried away from us faster and faster. Galaxies that are currently visible, galaxies whose light is reaching us right now, will eventually be carried beyond the observable horizon. Their light will no longer be able to reach us because the expansion will have accelerated them to recession speeds that light cannot overcome. This is not a sudden event. It is a slow, silent vanishing that plays out across billions of years. A galaxy at the edge of our current observable volume is already receding at enormous speed. As the expansion accelerates, that speed increases. At some point, the photons leaving that galaxy will never be able to close the growing gap between us. No new light from that galaxy will ever arrive. The last photons to make it will be stretched to extraordinary wavelengths, their energy drained by the expansion of space, their signal dimming to nothing. And then that galaxy will be gone from our sky forever. Not destroyed, not dimmed by distance alone, simply carried beyond the horizon by the expanding fabric of space itself. And it will not happen to just one galaxy. It will happen to all of them, one by one, the most distant first, and then progressively closer ones over the eons. The observable universe will shrink, not in absolute size, but in how many galaxies it contains. Objects currently visible will gradually fade and disappear as their light is stretched beyond detection and then beyond all possibility of arrival. In the far future, billions of years from now, any observers living in our region of space will see a dramatically emptier sky. The rich tapestry of galaxies that fills our current view, the spirals and ellipticals and irregulars scattered across every patch of darkness, will have been swept beyond the cosmic horizon by the accelerating expansion. The sky will grow darker, quieter, lonelier. Eventually, the only galaxies visible will be those in our immediate cosmic neighborhood. The handful that are gravitationally bound to us and therefore resist the expansion. The Milky Way and Andromeda by that time merged into a single, large elliptical galaxy, will be surrounded by a small retinue of satellite dwarfs. Beyond them, there will be nothing. No visible galaxies in any direction. Just blackness stretching to infinity. The evidence that the universe once contained trillions of galaxies, the deep field images, the redshift surveys, the luminosity functions, all of it will have become historical records of a richness that is no longer observable. Future astronomers, unless they have access to data preserved from our era, might conclude that the universe is much smaller and emptier than we know it to be. They might look at the sky and see only their own galaxy and a few companions, and reasonably assume that this is all there is. The cosmic horizon will have contracted, and the vast population of galaxies that fills our current sky will have vanished beyond reach. They would have no way of knowing what we know today. The universe would have erased the evidence of its own grandeur. This makes our current cosmic moment unusual, and in a real sense, privileged. We live at a time when the universe is old enough for galaxies to have formed and evolved into rich and varied populations, but young enough that enormous numbers of them are still visible. We can still see across billions of light years. We can still detect the cosmic microwave background. We can still reconstruct the history of the cosmos from its earliest moments to the present. This window of observational richness will not last forever. Dark energy is slowly closing it. We happen to live during the brief cosmic era when the universe can still be understood from the inside. That is not guaranteed. It is a coincidence of timing, and it will not persist. So let us step back and consider what the phrase trillions of galaxies actually means. Because it is one thing to write a number and another thing entirely to grasp its physical reality. Each galaxy in that tally, whether it is a grand spiral like the Milky Way or a tiny dwarf containing only a few million stars, is a real physical structure. It has mass. It occupies a volume of space. It contains stars that shine with nuclear fire, gas clouds where new stars might still be forming, planets orbiting these stars, dark matter holding the whole system together. Every galaxy in the count is a world unto itself, a vast complex of matter and energy operating under the laws of physics, evolving over billions of years. Some of these galaxies are spectacular, with sweeping spiral arms and brilliant star-forming regions. Some are ancient ellipticals, red and quiet, their star-forming days long past. Some are irregular and chaotic, disrupted by gravitational encounters with neighbors. Some are so small and faint that they would be invisible from just a few 100 million light years away. But every one of them is real. Everyone is there. And the majority of them have never been directly observed by any instrument humans have ever built. The galaxies that appear in our deepest photographs, the ones that fill the Hubble Deep Field and the Ultra Deep Field, The ones catalogued by large surveys, these represent only the detectable fraction of the total population. They are the brightest peaks rising above the cloud layer. The mountains tall enough to be seen. Below them, hidden in the mist, are far more galaxies than any image has ever captured. Small dwarfs too faint to register. Ancient proto-galaxies too distant for their stretched and weakened light to trigger a detector. Galaxies obscured by dust. Galaxies lost in the glare of brighter neighbours. Galaxies that fall into the narrow gaps between survey fields. The visible population is genuine and rich and beautiful in its own right, but it is a fraction, a minority, the tip of an enormous and mostly unseen distribution. When you look at a deep field image and see thousands of galaxies crammed into a patch of sky, smaller than a grain of sand held at arm's length, you are seeing something real and astonishing, but you are also seeing an incomplete picture. For every galaxy bright enough to appear in that image, there are others, possibly many others, lurking just below the detection limit. And below those, fainter still, there are more. The population extends downward into dimness, and we do not know exactly where it ends. The mathematical models suggest a boundary, a minimum mass below which gravitationally bound systems of stars do not efficiently form. But where that boundary falls is uncertain, and the population above it is already enormously larger than what any telescope has directly revealed. This is the deepest lesson of the galaxy counting problem. The universe is not merely larger than what we observe. It's fundamentally, structurally, permanently larger than what we can ever observe. The observable universe has a fixed boundary set by physics, not technology. And the galaxies within that boundary include a vast hidden population below any feasible detection threshold. Even within our cosmic horizon, the full population exceeds what instruments can capture. Beyond the horizon, the population extends further still, possibly without limit. The galaxies we count are a fraction of those that exist within our observable volume, which is itself possibly a tiny fraction of the galaxies that exist in the full universe. The old estimate of 200 billion galaxies was the count of what one generation of telescopes could see. The revised estimate of roughly 2 trillion attempted to include the modeled populations below the detection limit. Future telescopes will refine this number, pulling more galaxies into view and adjusting the statistical models that estimate the ones still hidden. But no telescope will ever see them all. The detection threshold can be pushed lower, but it will never reach zero. There will always be galaxies too faint, too distant, too small, or too deeply embedded in the noise for any instrument to find. And that is before you even consider what lies beyond the observable horizon. The regions of space from which light will never reach us. The volumes of cosmos that are permanently and irrevocably hidden. If the universe is infinite, then the population of galaxies is infinite, and the trillions within our observable bubble are nothing. A finite sample of an infinite whole. A single scoop of water from a shoreless ocean. This should not make you feel small, though it might. It should make you feel something deeper than that. Or perhaps, or wonder. Because the fact that you know this, that you can sit here and contemplate trillions of galaxies stretching across billions of light years. Galaxies you will never see with your own eyes. Galaxies whose light has been traveling since before the Earth existed, is itself extraordinary. You are a collection of atoms on a small rocky planet, orbiting an ordinary star in one galaxy among trillions, and yet you can comprehend the scale of the cosmos that produced you. You can hold in your mind, even if imperfectly, the idea of 2 trillion galaxies. You can understand why that number is uncertain, why it changes over time, why it depends on how you observe and what you define as a galaxy. You can grasp the distinction between the observable universe and the universe as a whole, and appreciate that the former might be an infinitesimally small fraction of the latter. No galaxy in the sky understands this. No star burning with the light of nuclear fusion knows how many other stars exist. No planet spinning in orbit around a distant sun comprehends the vastness of the cosmos. But you do. Or at least you can try. And that capacity, the ability of matter to organize itself into structures capable of understanding the universe that gave rise to them, might be the rarest and most remarkable thing in all the trillions of galaxies that fill the darkness. Consider what had to happen for you to be here right now, contemplating these questions. Hydrogen atoms formed in the first minutes after the Big Bang. Gravity pulled them together into the first stars. Those stars burned through their fuel and exploded, scattering heavier elements into space. New stars formed from that enriched material, and around some of them planets coalesced from the debris. On at least one of those planets, chemistry became biology. Single cells became complex organisms. Brains evolved that could wonder about the lights in the sky. Civilizations rose and built instruments to magnify those lights, revealing not just more stars, but entire galaxies. And not just a few galaxies, but trillions. 13.8 billion years of cosmic evolution, from the first hydrogen atoms to this moment, produce beings capable of counting the galaxies and recognizing that they could never finish the count. That chain of events is extraordinary by any measure. And it happened here, in one galaxy, on one planet, as far as we know. Whether it has happened elsewhere, whether there are other minds under other suns contemplating other deep field images, is a question we cannot yet answer. But the mere fact that it happened at all, that the universe produced something capable of wondering about itself, suggests that the trillions of galaxies filling the darkness are not just objects to be counted. They are the context in which consciousness arose. Without them, without the billions of years of stellar evolution and galactic merging and chemical enrichment that built the elements we are made of, there would be no one to ask how many galaxies exist. The question and the questioner are both products of the same cosmic process. The next time you look up at the night sky on a clear, dark night, try to see it differently. The stars you observe are all part of the Milky Way, a single galaxy among trillions. The dark spaces between those stars are not empty. They are filled with galaxies beyond count, each one a vast system of stars and worlds, most of them far too faint and far too distant for your eyes to detect. The deepest photographs ever taken have revealed thousands of galaxies in patches of sky, smaller than a grain of sand. And even those photographs captured only a fraction of what is truly there. The universe is filled with galaxies, not hundreds of billions, trillions, perhaps more, stretching across 93 billion light-years of observable space and almost certainly extending far beyond into regions we will never see, carrying populations of galaxies we will never count. The visible galaxies, the ones that appear in our images and fill our catalogues, are only the detectable peaks of a far larger cosmic population. The mountaintops above the cloud line. Below them lies an entire landscape of galaxies that no human eye and no human instrument has ever directly observed, and quite possibly never will. That is what trillions of galaxies means. Not a final number, not a settled count, but a window into a cosmos so vast, so richly populated, and so far beyond the limits of direct observation that even our most ambitious estimates are almost certainly incomplete. The universe is not merely large, it is larger than we can see. It is larger than we can ever see. And the galaxies within it, born from the primordial fog, shaped by billions of years of gravity, merging and evolving across cosmic time, are more numerous than any single number can capture. The darkness between the stars was never empty. And the universe we observe, extraordinary as it is only the beginning of what exists.